Okay, let's get started. Welcome, everybody. So this is the second year of our Science and Cooking lecture series, and we're going to have a whole series of lectures. I should acknowledge right at the start, as I will each time, that we're very fortunate to be sponsored by this group of organizations. Jose Andres, who, by the way, will be one of the speakers. The Alicia Foundation has been integral in helping us both financially with support and intellectually with the class that this lecture series is associated with. Montferrand, Whole Foods on River Street. Ulaba provides some of the important constant temperature baths that we use in our class, and this bank helps support Alicia. So this is a lecture series that's associated with a class that's offered here at Harvard. I'm Dave Waits. I'm teaching the class. I have very, very able assistance by a large group of people who are working on it. The lectures that we'll be hearing are all associated with one of the lectures of the class. So this class is Science and Cooking from Haute Cuisine to Soft Matter Science. It's really a science class as well as a class about cooking. And we do both in the class. So for example, the class today had a review of math that we're going to use, a discussion of scientific rigor, and a discussion of the historical context. Now, the public lectures, of which this is the first, are always associated with the class, and this is our way of trying to share some of the renowned chefs and other visitors that we have with the rest of the Harvard community. So we're going to have a series of great chefs and great lectures. Most of the time, the lectures will be on Monday, but we have today's lecture on Tuesday because of the holiday yesterday. We're going to do things slightly differently than we did last year. This is a series of lectures associated with the class, and the class is really a science and cooking class. And so we're going to have a little bit more explanation of some of the science that goes along with each of the chefs. I think we're slightly better prepared, so we can do this perhaps a little better than in the mad rush that we did last year. And so we want to try and relate what the chefs have to say to some of the science that we teach in the class. So I should remind you what I reminded the class. This is the second year that we had the class. Last year we had a new class, we had new traditions. And so I expect the same for these public lectures. Every time we see a great dessert, and we'll see many of them today. This is an example of one of the great desserts that was made in the lab. One of the fun things about this course is that we get to eat the lab. So we could eat this lab. But every time we see a great dessert, we clap. And this is a science class, so every science class has equations, and this is one of the examples of one of the equations that we will discuss in class, and if you come to these lectures, we'll discuss in these lectures. And since this is really a science and cooking class, every time we see equation, we clap. So for somebody like myself who's been trying to teach physics to undergraduates for years and years, I'm very proud of the fact that I can actually get people to clap when they see equations. So next week, the lecture will be on Monday, and Joan Roca, one of the wonderful chefs from Barcelona, will be discussing, he'll talk about precision cooking. He'll use some of the modern apparatus that people use in kitchens. We'll see a little bit of that today. And so today, without further ado, I'd like to introduce the people who are responsible. First of all, I'd like to introduce Pia Sorensen, who's really helping a lot with the class, and we couldn't do the class without her. So Pia, thank you. And the speakers today are Harold McGee. Harold actually literally wrote the textbook. He wrote the textbook that we use in class. We're really exceptionally fortunate that he's going to contribute to the class with a series of lectures. He'll offer the first lecture today, but he'll be back several times in the class to help us teach people. And he really is extremely knowledgeable about both the relationship, about both cooking and the relationship of science to cooking. And Dave Arnold is an excellent person for demonstrations, and I hope we're going to see a whole lot of really fun demonstrations. So without further ado, Harold.
All right. Thank you. Thank you very much. Wonderful to be here. Thank you, Dave. And I'm especially delighted to be here talking to you about this subject because I first started writing about this subject right around here. I wrote the first edition of On Food and Cooking in Cambridge. I'll show you one of the libraries I worked in a little bit later on. I never dreamed in the late 1970s that Harvard would ever deign to give a course on cooking. So times have changed, and I'm delighted I can make a living now. And just an extra word or two about Dave Arnold. Dave and I met maybe 7, 8 years ago, and he is the Director of Culinary Technologies at the French Culinary Institute in New York. And he, as far as I'm concerned, is the one guy in the world who knows the most about the use of cutting-edge technologies in the modern kitchen. And he's going to be showing us some of those things well, sprinkled throughout the lecture, where, as you'll see, some things are not quite where they're supposed to be at this point in the evening, but we'll figure something out. Anyway, what I'm going to do is just give you a very quick surf through culinary history from the perspective of science, just to talk about the way that science and cooking have influenced each other, some of the good things that science has had to offer to the kitchen, some of the not so good things that it has had to offer, some of which you still hear all the time. And then I'm going to give you a brief introduction to this very interesting moment in culinary history. The last 20 years have been really fascinating and has to do with a real shift in the way professional chefs view their vocation. And because you're going to be having a parade of remarkable chefs coming through Cambridge beginning next week, I'm going to tell you a little bit about how this movement has come about and a little bit about a few of those chefs, just so that you have your appetite whetted and you come back for all of those lectures. So I'm going to start with something that Dave asked me to do because we realized in talking about the beginning of the course that nowhere in the course was cooking defined. The course is about cooking, and we hadn't bothered to just ask ourselves, well, what is it really that cooking is? So Dave suggested that I provide a definition to start out with, and then he, from the perspective of science, is going to modify that. We'll have a conversation about it, and who knows where we'll end up by the end of the course. But this is where we're beginning. Essentially with the dictionary definition, the preparation of food for eating, especially by means of heat. But the term, the word, English word, comes from a Latin root, which I think is very suggestive. The root means those things, but it also means to ripen, as in the case of fruits, and it means to digest, which are two other transformations of edible ingredients. One is done by the plant that produces the fruit, or the fruit itself, and the other is done by our body in the process of assimilating it. And it seems to me that there's something in there to think about that's very interesting. What is it about the preparation of food for eating that gets us so interested in it? Why are there so many people here listening to a lecture on food? I mean, we love it, and we love cooking. We loved cooked foods. Why? And it seems to me that the fact that the root comes from a word that includes the process of ripening is a clue. Daniel from back here brought me a peach to show you, because many chefs these days will say They do amazing things, the kinds of things that Dave is going to demonstrate in order to delight and surprise you. But they'll also say, you know, if this peach is perfectly ripe, then the best thing you can do with it is put it on a plate with a knife and a napkin to mop up the juices. A fruit, in a way, is a perfect food. And it is that way because it was designed to be that. It's one of the few things in nature that we're actually meant to eat. The plant wants us to eat them so that we'll take the seeds with us and plant the seeds far away from the parent plant. So these are concocted, these are cooked for us by nature. And it seems to me that a lot of what we do in cooking is an attempt to in some way approach the deliciousness, the complexity, the balance of a perfectly ripe piece of fruit. That said, cooking does things that nature can't do, and can you smell what Pia is taking care of over here in the back of the room? What's going on in that pot? Caramelization. So I don't know if I left any sugar in the container, probably not, but you all know what sugar looks like. It's white crystals. It's a single pure molecule, one molecule. You take that one molecule, you put it in a pot, you add heat, and that one molecule, first of all, the crystals melt and they start to bubble. So the physical state changes. The color changes, and of course you end up with this amazing aroma, which you can smell a mile away. This to me is also the essence of cooking. It's taking matter and applying human ingenuity and energy to transform it in a way that makes it more interesting. And to me, this is the best example of culinary alchemy, that you take one molecule, you end up with thousands of molecules that give us this room-filling aroma. And we're probably getting close to burning it, right, Pia? So we can stop there. Okay, good. Okay, so a little bit now about the development of cooking and its science. I went into much more detail this afternoon with the class about when it was in history, the different kinds of foods appeared, when we figured out how to work with sugar, when we figured out how to make emulsions, when we figured out how to make thickened sauces. All of these things are topics that are going to be covered in the course. I'm not going to inflict all of that on you, but just a couple of examples, of course, beginning with fire. That's all that was really going on here, the application of heat energy to transform matter. And of course, that made cooking possible. Richard Wrangham here at Harvard has advanced the hypothesis that maybe that's also what made humanity possible. He's written a book that argues that what allowed Homo erectus to evolve into Homo sapiens was the invention of cooking. By cooking roots, for example, you can get starches to turn into something that are actually digestible. Pure starch, raw starch, is not digestible. Cook it and it is, and you can get all those calories. And we needed calories to develop these big brains. So it's a really interesting argument. Lots of pros and cons. People in his field, some of them believe it, some of them don't. But it's fascinating. It's going to be fascinating to see how it develops, because the question now is, how far back can you find evidence of cooking? At the moment, we're only maybe 100,000 years ago. He's saying it's more like 1 million years ago. And so it's going to be interesting to see what anthropologists are able to find. Just a quick picture snapshot from the Middle Ages. That's a time when people figured out how to make gelatin jellies. And they went into great detail into how to clarify them and then make them into decorative things for the court. But they also were very interested in food as entertainment. And that's something that's come to the fore in the last 20 years or so. I just want to show you that it's nothing new to use liquid nitrogen and lasers in the kitchen. So this is the 15th century, sorry about that, the 15th century version of that kind of showmanship, a recipe for how to make a chicken squawk while it's on the spit. And you notice that it involves sulfur and mercury in the chicken. Not such a great idea, probably, but we've learned some chemistry in the meantime, but nothing new about using food to entertain other people. And now about some of the contributions that science has really made to cooking. And you can go back to the Royal Society at a time when Isaac Newton was a member to find the first instance of that. And so this is a man named Denis Papin. And do you recognize what the machine is in that slide? Pressure cooker. So the pressure cooker goes back to the 17th century. And it was developed because at the Royal Society were a number of men who were responsible for developing the gas laws, the relationships between pressure and temperature and volume. And Denis Papin was working for one of those men, Robert Boyle, and got the idea of putting that information to use and making a device that would be a much more efficient way to cook than cooking over an open fire. So he realized that if you could make a container and manage to clamp it shut and boil water inside it, that the pressure would build up and therefore the temperature would build up and you'd be able to cook things much faster. So this was, a real innovation. There had been no cooking like this on the face of the earth up to this point, and the members of the Royal Society who experienced it really did talk about it as a completely new experience. So the members of the Royal Society were mostly bachelors. They dined with each other, usually at each other's lodgings, and every once in a while after he developed the digester, the pressure cooker, they would meet up. Papin would bring along his digester. It's kind of like a Tupperware party or something. And other people would bring ingredients, and they would see what the pressure cooker would do to them. And we have these wonderful diary entries. I won't bother to read it, but just you can see that he's just exclaiming. He says, "This is great, and this was like nothing else I'd ever had before, but then neither was this, and neither was this." They'd never been able to eat bones as if they were like nothing but cheese. So it was a new experience of food made possible by scientific understanding of the nature of the universe. Now, at this point, we had planned to do a demonstration. Oh, no, another couple of, right, sorry.
Show this stuff.
Right. After the next one.
You want to talk about the pressure cooker? We're going to talk about the pressure cooker, the new stuff.
Okay. Right.
Yeah.
Right. So.
Don't have to.
If you read what the diarists said in the 17th century about the pressure cooker, of course, to us it's kind of old hat. I've actually never cooked a bone to see what it's like with the consistency of cheese, but I do know, and I use the pressure cooker to speed up cooking. All that kind of thing is fairly straightforward. But in this time, when chefs are looking to find new ingredients, new techniques, but also looking at old pieces of equipment, familiar pieces of equipment, and finding new things to do with them, people have been doing really interesting things with pressure cookers recently, and Dave has been at the forefront of this.
Well, pressure cooker is extremely interesting because they're one of the things that fundamentally alters the way you cook, because by altering the pressure, we're altering the temperature at which things cook. So there's certain things can happen at those elevated temperatures that you can't get in water normally unless you apply pressure. But no one has really spent the time until the past couple of years to carefully observe what's going on in a pressure cooker to try and use some of those effects to good advantage. There's a famous cookbook author, Lorna Sass, who wrote a book called Under Pressure, like I think it was what it's called, right? Mm-hmm. The Real Under Pressure, not Thomas Keller's book, Under Pressure. No offense to Thomas Keller's book on pressure on vacuum cooking, but she had made a comment, and she said that you need to add a lot of onions to things when you pressure cook them because the onion flavor dissipates. I said, well, that's interesting. So I cooked some onions, and Sure enough, the flavor dissipated. So we cooked some stuff that are similar to onions, garlic, and the flavor dissipates. So it turns out if you pressure cook garlic at 15 psi, which is roughly 250 change degrees Fahrenheit, as opposed to 212, which you're normally boiling at, all of the stuff that makes you stink the next day in garlic goes away. So you can eat clove after clove after clove of it, which you wouldn't normally do because it's mushy, because the texture is mushy, but you can blend them into a sauce and you don't stink the next day. You can take, we were going to do this, but it turned out to be a nightmare, so we didn't do it. You can take onions, and you can pressure cook them, and they've lost all of the pungency of an onion, and all that's left is the sweetness. So you can actually make an ice cream out of this. So we tried other things. Both of these things have sulfur compounds in them that are responsible for their pungency. So we chose something else that was similar. Horseradish. Horseradish knocked out. So you can take horseradish and you can have horseradish that is, you could just eat by the bushel, the horseradish. It's delicious. Also, there are things that have sulfur compounds but also get texture modified, like onion seeds, mustard seeds rather. You take mustard seeds and you pressure cook them with vinegar and they puff up like caviar and you can pop them in your mouth. But also, they're pleasant to eat in large quantities as long as you mix some sugar in afterwards. So there's all sorts of new things you can do. Like we can speed up Maillard reactions in certain things like eggs. So if you take an egg and you pressure cook an egg for an hour or so, right, because the egg is alkaline, you can get browning, a Maillard reaction in it that you couldn't possibly get unless you cooked for several days in a normal technique. So there's all sorts of new things you can do with a pressure cooker to modify texture, to modify flavor, if you observe carefully what's going on every time you put something in and out. Here's something you might not have known. How many of you own a pressure cooker out there? Good. Thank God. Now listen, when you make a stock with pressure cooker, I'm not going to go into the ins and outs because it's very complicated, but do this. If you take a made stock, already made stock, put it in a pressure cooker and close it, right, and cook it, it comes out browner than you put it in. Like, things happen in the pressure cooker. This is basically like observing those kinds of things and what's going on with the taste, tasting side by side, paying close attention is how you come up with new techniques for a piece of equipment that's been around for a long, long time.
You're here. So that's the pressure cooker. And that's just the half of it. I mean, you didn't go into the durian. You didn't.
Oh, no. Oh, you can go into the durian.
No, it was your experience.
So during the class today, they're trying to teach the students that repeatability is vitally important, and taking records is vitally important, and it's being careful with your measurements and your recording, which is true. So one of the best things I ever made in my life was durian. You guys familiar? The super stinky fruit. Yeah, like hyper stinky, like you're not allowed to bring it into your hotel room, but everyone who loves it, and it's fantastic. So when you cook durian, which also has a lot of these kind of sulfury notes to them, you can unstink it in a pressure cooker. So people who actually grew up on durian and who love the stink don't like the pressure cooked durian because they're like, where's the stink? But most people like it. And I randomly threw some stuff in to run a test on it, and I didn't record anything. I didn't record the time. I didn't record the amount of durian that went in. I didn't record the liquid that I had added. And the result was the most delicious durian caramel. It was unbelievable. I was so psyched. And I ran a month of tests to try and recreate what I had done without having the records, and was unable to do it. So one of the best things I've ever made, I will never make again, most likely, because of poor record keeping. So don't be a schmuck like me. Keep records. Yeah.
All kinds of lessons there. So, okay, moving on from the pressure cooker to an example of something that is going to be a recurrent theme in the course, that you can learn very interesting things about the way the world works, often from the simplest observations and minimal calculations, using some math, but not having to remember anything about calculus, for example. Just arithmetic. So here's an example. Benjamin Franklin, back in the middle of the 18th century, could have figured out very easily how big a molecule is. 110, 120 years before people agreed at last that there were such things as molecules, he could have, he essentially did measure the size, but didn't go on to calculate it. What happened was that he did a lot of traveling back and forth between the States and Europe. He was often in a flotilla of ships, and he noticed that whenever one of the ships in the flotilla was the cooks were dumping the garbage from preparing food, that the wake was calmed behind the ship. So oil being poured on troubled waters. The water was calmed. He was very interested in that phenomenon, as he was interested in many phenomena, and he decided to do some experiments to try to figure out what was going on. And one of them was this one. He went to this pond just outside London, Clapham Pond, and he took a teaspoonful of oil on a windy day and put some near shore, just poured it very gently to make sure it would stay on the surface. Of course, oil and water don't mix, oil floats. And so he put a little oil, a teaspoon of oil on the water. The wind then blew it into the middle of the pond, and he observed how big a patch he was able to calm with that teaspoon of oil. And the answer was about half an acre, about half the pond, which he estimated at an acre. So, and you know, where it stopped, you figure, well, that's where the oil stopped. So there aren't any molecules of oil past that, or there isn't any oil substance past that. So what's left is the original volume of oil spread out into as thin a sheet as can possibly be made. And it turns out that that's a really good way to figure out how thick one molecule of oil is. And so we went through the calculations. Lots of equations on that slide. To demonstrate that he could have figured out very easily, just by the simplest of arithmetic, that a molecule of oil would be about 1 nanometer, which is within a factor of 10 of what it really is. So just a demonstration of observation and calculation leading to real insights into the way the world works. Now, at this point, oh, it's going to work, okay?
Well, I don't know. It might work.
Okay. So we've got a demonstration that speaks somewhat to the same point, that you can, in the kitchen, doing sort of everyday things. This is not every day, but making mayonnaise, for example, similar sort of thing. You can end up with a mass of material and end up dividing it into astronomically large numbers of particles, or fibers in this case.
Yeah, so we're going to try to make a traditional kind of dragon's beard candy, which is there's actually, there's a dragon's beard is what they call it in China. There's one that's from Turkey. There's one from Iran. They're all fairly similar, and it's basically sugar that's cooked to this texture, and the texture of it is vital. And so since I was disorganized and didn't cook it till too recently, we're on the edge of it not working. But the theory is that I can pull it, and by putting a little bit of cornstarch, in this case mixed with cocoa powder, just add a little flavor, as I pull, that we can keep the strands separately, and just by dividing it again and again, we can make an ungodly number of strands. Ready? That's what? 2? It's a little stiff. We'll see whether she... We have 4. It's a little stiff, Harold. We might break it, but I hope not.
Okay, so we're 4 strands. So we're just doubling the number of strands with every turn.
So she's a little stiff.
Okay, up to 8. Similar kind of thing happens when you make puff pastry. $16.
The guys who are good at it, they get the texture exactly right, and it's much faster and more fluid, but they do it every day. I think it's a good trade. Let's see.
32.
The real trick is to never, ever let go of it at any point, because you'll start losing strands. As long as one hand is always on it, you should end up not being too horribly off. What am I at now?
64.
All right, so now it's going to start picking up, yeah? And I didn't follow my own rule, and I lost a strand. Jerk. Where are we, Harold?
Okay, 128.
Any guesses what I'm going to take this guy up to?
Ah! 256.
Hmm.
512.
My first Macintosh. That dates me, huh?
Okay, 1024. So from one strand to 1,000 in a minute and a half. 2048. 4,096. 8,192.
Good with the on-the-fly math there.
All right, this is 15, so 16,284.
And that's where I'll keep it. Let me stretch it out a little bit. So what do you calculate this out at, Harold, the average fiber width?
So if the initial rope is 1 centimeter in diameter, then these are going to be about a micron.
I'm going to let it dry out a little bit before I serve it so that it separates out better.
You want to say what it's used for?
You eat it. Typically it would be done with an unflavored coating on the outside, and they would wrap something like chopped peanuts in it. The chocolate's good. My actual favorite is vinegar powder with vinegar powder and mustard powder and a little bit of cornstarch mixed, and then with peanuts wrapped in the inside. It's incredibly delicious. But I didn't order all the stuff because I'm disorganized. Sorry.
All right, so astronomical numbers and tiny sizes from big things. It's amazing transformations take place in the kitchen. Another example of science making a real contribution to the kitchen. Unfortunately, this one was forgotten until about 20 years ago. Benjamin Thompson, Count Rumford, a New Englander, during colonial times, he made the mistake of choosing the wrong side in the Revolutionary War, and so he spent most of his career in Europe. But he did some amazing things. I think he deserves to be remembered as much as Benjamin Franklin for his contributions to our understanding of things. One of the things he was interested in was heat, and he, for example, was the first person I'm aware of to describe heat transfer by convection in liquids, because he wanted to know why he kept burning his mouth on hot soup. So he was that kind of curious character. He was very interested in energy-saving modes of cooking, and so the machine up there was designed originally to dry potatoes. One day he decided that he would try cooking meat in his potato dryer just to see what would happen. The potato dryer works, I mean, you don't want to cook the potatoes, you just want to dry them, so it was probably operating at 140, 150, 160 degrees Fahrenheit. And he just decided one day to put a leg of mutton into his potato dryer and see if he could cook it. And he left it in there for several hours, checked on it. It seemed as though it was still pretty much raw, so he decided that experiment was a failure, closed it, locked up his workshop for the day and went home, and then came back the next morning, and there had been enough residual heat in the potato dryer that he said when he opened the door to his workshop, he was greeted with this amazing aroma. He then checked the potato dryer, and he said the leg of mutton in there was the best he'd ever eaten. So he discovered the principle of low temperature meat cooking in 1800 or so, something that was only discovered by chefs maybe 10 or 15 years ago. He, I think, is a model for the way scientifically minded people should approach things in the kitchen, because rather than just resting on his laurels and saying, you know, I've discovered this amazing thing, he decided to double check to make sure that, you know, what he observed was a real phenomenon. So he did several more experiments. One was to compare a leg of mutton with another leg of mutton trimmed to the same weight that had been cooked over a fire in the traditional way, to the leg of mutton cooked in his potato dryer. So 2 legs of mutton cooked 2 different ways. He weighed them before and after. He discovered that the one that had been done in the potato dryer, sure enough, had several ounces of water, or several ounces more weight left in it compared to the one done over the fire. And then he did what I think is the first taste test in history. So he threw a party, and he put 1 leg of mutton at one end of the room and the other leg of mutton at the other end of the room. And at the end of the party, he weighed what was left. And he reports that there was pretty much nothing left of the leg of mutton done in the dryer and lots left over from the one done over the fire. As I say, this is something that chefs now take for granted, but for whatever reason, that discovery was just kind of overlooked. I think partly because he was doing it in Europe and wasn't a famous guy, and it just, the word just never got around. Anyway, he's, I think, a good role model in that way. The worst role model I can think of for someone interested in understanding what's going on in the kitchen is this man, a scientist, Justus Liebig, a chemist, eminent chemist in the middle of the 19th century, worked in Germany, took an interest in all kinds of things, as did Rumford, but Liebig was not so much of an experimentalist. So he would come up with theories and then decide that, well, because he was Liebig and it was his theory, it was probably correct. So he came up with a theory in this book, Researches on Food, that if you wanted to keep the moisture in a piece of meat, then rather than doing what Rumford had discovered actually works, what you should do is sear the outside at a very high temperature to seal the juices in. And I think his model was probably cauterizing or something like that. You know, you take something, you seal up the pores so that whatever's inside can't get out. That's an interesting model. Turns out it doesn't apply to meat. But he published this book anyway. As far as I know, he never did an experiment. And unfortunately, the book was hugely influential, because this was right at a time when the cookbook industry was on the rise, and there were multiple editions by the same author being published year after year, and people were looking for ways to distinguish themselves from the rest of the crowd. And so here's this guy, eminent scientist, comes out with a new revolutionary way of cooking meat. By the way, it's the reverse of what was done traditionally. You would roast things far away from the fire to begin with until it was cooked through, and then at the very end you would brown it just before serving. He was saying to do it the other way around. So new guy, new idea, good background, good credentials. So cookbooks started revising themselves and presenting his theory as being fact. And in fact, it wasn't fact. So anyone who's cooked a piece of meat properly so that it is still juicy knows that the juices come out no matter how hard you sear it on the outside. I gave a talk once at the Confederation of Canadian Chefs, so a room like this with lots of high hats, and I asked a show of hands how many people believe that searing meat seals in the juices. This is maybe 10, 15 years ago. 90% of the hands went up, and then I put this slide up and said, how many people have seen this when they've cooked meat perfectly? A few hands go up. And then how many people still believe that searing meat feels? So at least I convinced that room. You know, room by room, I'll be able to do something about it. but you still hear it on TV shows and in magazines all the time, searing meat, seals, and the juices. There was a long period, kind of fallow period for science in the kitchen that has to do with a variety of things. Home economics is one of them. There's a wonderful book on the subject, Perfection Salad by Laura Shapiro. World War I, all kinds of things kind of diverted the attention of scientifically minded people away from what happens in home and restaurant kitchens and toward industry. And that has sort of been the case for, or was the case for many decades. Finally, in the 1960s, an eminent scientist in England took an interest in delving into the physics of cooking. He loved food, he loved to cook, and he realized at some point that he had a real contribution to make because no one had really talked about this. And in fact, he gave a lecture at the Royal Institution of London, an institution that Count Rumford actually started back in the 19th century, in which he said, it's a sad reflection on our society that we know more about what's happening on other planets than what's going on in our own kitchens. And so he started to try to do something about that. And this graph is one example of that, trying to find out what is going on inside our soufflés. He made a soufflé in his home kitchen, put a thermocouple from his lab into the center of it, and then watched the temperature change as it cooked. And what he noticed was, and for whatever reason, time 0 is at the right of this chart, and it being done was at the left. The temperature rises on the inside, and then it plateaus, and then it starts to go up again. And what he discovered by trial and error was the perfect texture was at that point just before it begins to rise again. And that plateau is a phase transition. The proteins are denaturing and beginning to coagulate. You're getting a change of phase. That's why the texture changes. And that's one of the subjects that the course is going to go into in great detail. So here's an example of someone really pioneering not that long ago in understanding exactly what's going on there. Then I have to get a little personal about it because thank you. In 1976 or 77, I first came to Cambridge with the idea of writing a book about the science of cooking, and found, to my surprise and delight, that I couldn't have picked a better place to come, because the Schlesinger Library is this amazing treasure trove of books about the household in general and cooking in particular. And so I spent hours and hours and hours over there learning about the history of different techniques, uses of ingredients, when people figured out different sorts of things. That's where I discovered Liebig's malign influence on people who cook meat, because I was able to march down a shelf and see all of a sudden this guy Liebig is being mentioned, and the cooking of meat is now different. So I'm tremendously grateful to the Schlesinger Library for existing. And I was able to write a book, and also discovered around that time the pleasure of engaging in that kind of science myself, doing the kind of thing that Nicholas Curti had done a couple of decades before. And the very first experiment I did had to do with a statement of Julia Childs, also a Cambridge denizen, in Mastering the Art of French Cooking, saying that if you're going to make a soufflé like Nicholas Curti's, or a meringue or something like that, and you're going to whip egg whites into a foam, you should use a copper bowl, because copper acidifies the egg whites and makes the foam more stable. And when I first read that, I thought, well, that doesn't make any chemical sense. Metal is not going to change the pH of the egg whites, and so there's probably nothing to this. It's probably an old cook's tale. Forget about it. And I did forget about it and didn't write anything about it until shortly before my book was going to be published, and I was on the search for inexpensive illustrations to put into my book, because my sister had done line drawings, but there was still big blocks of text that we wanted to break up. So I found an old French book about different professions, and one of those professions was pastry cook. And there was a plate in that book showing a pastry kitchen, and in that kitchen a young boy whipping like this. The plate had a key, and the key said that the figure under number 8 was whipping egg whites to make biscuits in a copper bowl. So I thought, well, if it's being said in 1770 and Julia Child is saying it in 1970, maybe I should take a look after all. And so I did the experiment I should have done in the first place and found, as you can see, that there's a tremendous difference. The color is different, the consistency is different, the stability is different. It takes 3 times as long to do it in a copper bowl as in a glass bowl. Everything was different, and nothing was known about the chemistry. So some friends and I tried to figure it out. Wrote up a paper for the journal Nature. They sent it through their regular review process. I think it's the only paper they published that quotes Julia Child, and we quoted Plato, who said we needed to know more about what's going on in the kitchen. Sent it through the review process, and it was accepted. One reviewer said, the science is fine, but the subject is fluffy. So, I'll take that. So for me, and this is why I brought it up to the students today, for me this was an example of how easy it is to be fooled by your own preconceptions into missing something really important. So cooks are amazing. They have an amazing bank of sensory information about the way foods behave in the kitchen. And I never, not since that day, have I ever discounted what I hear from a chef. You know, if a chef tells me, you know, if you add parsley stems to the cooking water, it keeps things green, I doubt it, but I'll go try it, because you never know. Anyway, a few years after that came gatherings of chefs and scientists in Sicily, and this is where the term molecular gastronomy came from. I think it's a really unfortunate term. It was a marketing term to try to get the scientific conference center to accept cooking as a reasonable subject for holding a conference. They said, we can't call it the science of cooking. Give me a better title. We came up with molecular gastronomy, and had we known that it was going to have this kind of afterlife, I don't think we would have proposed it. But this picture is especially interesting to me because, in addition to having a much younger me in it, over there, and Nicholas Curti at the center stage, there's this man. He was a French physicist, and he's the man who gave the name to the science that's being taught in this course, soft matter science, or soft matter physics. So his name was Pierre-Gilles de Gennes, and he won the Nobel Prize in 1991, essentially for studying phenomena that until that time really weren't that respectable in the physics community. I mean, you studied particle physics. That was the real thing. You didn't study soap bubbles, which part of his Nobel lecture was about, the physics of soap bubbles. And he just demonstrated by analyzing things carefully and presenting that analysis that the physics of everyday life is every bit as challenging and maybe more challenging than the kind of standard physics that was being done at the time. He had to come up with a name for this sort of the physics of everyday life, and the name he came up with was soft matter. And he says in this quote that, you know, you have to find the right name for fields like this, otherwise you're going to scare away good students who might otherwise make real contributions. Okay, so that's it about the science part. Now what I'm going to do is tell you very quickly about the evolution of haute cuisine. The course is about the science of cooking from haute cuisine to soft matter science. And many of the chefs who will be coming in the rest of the series are playing a major role in redefining haute cuisine these days. So I want to tell you a little bit about how we got to this point, and then a little bit about those chefs. So first of all, there's nothing new about innovation, nothing innovative about innovation. This slide from the middle of the 18th century is the first one I know of, first use that I know of for the term nouvelle cuisine. We associate that more with what happened in France in the 1960s and 70s, but in fact people were thinking about nouvelle cuisine in the 18th century. And what this mention of it is about, and there are other citations I could give you, is really about the transition from medieval cooking to what we would now call classic French cooking. So the original nouvelle cuisine was classic French cooking. Get rid of all those spices, get rid of all the vinegar, make things that are balanced and delicate, mainly based on meat stocks. Veal stock, beef stock, chicken stock. Those are the bases for most of the classic French sauces. So that was nouvelle cuisine. The exponents of classic French cooking in the 19th and 20th centuries were Carême and Escoffier. They really codified haute cuisine, classic French cooking, and codified it to the point that there was really no wiggle room for chefs to do what might move them. So just as an example, if you go to Escoffier's Guide Culinaire and you ask what recipes does he have for slices of beef tenderloin, he has more than 100 recipes for that one cut of meat. There are something like 4,000 recipes in the whole book. More than 100 recipes. He tells you how thick the slices should be. He tells you that they need to be on croutons that have been fried in butter. He tells you that you use this sauce if you have this accompaniment, and that sauce if you have that accompaniment. Everything is laid out, and people expected this. You go to a French restaurant in Paris, and this is what Escoffier says, this is what it should be, and you're measured by how well you meet the standard. You can imagine that that might be discouraging to people who wanted to do something different. And so in the, let's see, did I miss one there? No. In the 1960s and 1970s, a virtual dessert. No equation, right? I didn't. He's the guy who invented the melting chocolate cake. How many of you have had the chocolate cake with the sauce inside? So, yeah, Michel Bras is the guy who invented it. And it's something that he's remembered for all over the world. He's revered as a chef in the profession of chefs for being someone who took up this challenge of taking back cooking to the chef himself and not to the book on the shelf that tells you how you're supposed to do stuff. So he was a French chef, a very good French chef, he's still alive and very active, who set aside Carême, set aside Escoffier, and took his own route. And so in classic French cooking, if you're going to make a cake, you make a cake. And you put a sauce around it. You don't have the sauce in the cake. He made it the hard way by making a ganache and putting the ganache inside the cake and then working out the timing so that just as the cake is getting cooked, the ganache is melting. There's actually a much easier way to do it, which is just to undercook a properly made dough or batter. And that's what the class is going to do. They're going to be studying heat transfer by making this dish. But it's an example of the kind of freeing up of the creative process that took place in the nouvelle cuisine of the 1960s and 70s. Another dish that he is remembered for in the profession, although I think this hasn't been as widely influential as the chocolate cake, is the gargouilloux, which is salad. It's kind of a vegetable salad. What distinguishes it is that he lives in the Auvergne, out in the country, and he decided, the heck with these composed salads of carrots and turnips and this and that. I live in a part of the country where there are all these amazing things growing along the path when I go for a walk in the morning. I'm going to make a salad out of what I see every day. And it's going to change every day depending on what I see. And so he made this dish. Gargouillou means essentially just mixture. It's a local dialect term. And it's you know, the salad as the chef wants to make it based on what he's got available on that particular day. Again, that doesn't sound terrifically innovative to us on the other side of it, but it was a revolution at the time, and had a tremendous impact on the thinking of other chefs in the world. One of those chefs is responsible for the spirit of cooking that's going on today, this kind of experimental spirit. And he's in this picture. So this was taken in 1987 in kind of full nouvelle cuisine mode. And there was a chef there by the name of Jacques Maximin. He's the one not wearing a toque, wearing jeans instead of a uniform, and a jacket instead of an apron. And he gave a talk at this meeting of chefs in which he said, to be really creative means not copying. Again, doesn't sound like a remarkable aphorism, but it really struck a chord with this guy, whose name is Ferran Adrià, and who has said ever since that that was sort of the moment that he fell off the donkey and it changed his life. He said, okay, I'm going to take that seriously. I'm going to really not copy. I'm even going to try not to copy myself. I'm going to make something different every year. And what that did for the profession of chefs was to allow them to step back and say, we have all these wonderful traditions, and it's wonderful to be a French chef or a Spanish chef, but this is a different world now. We can get any ingredient from anywhere in the world. We are understanding more and more about the basic principles involved in cooking. We can use techniques from Asia. We can do anything. So why not explore all these possibilities and see what we can do that hasn't been done before? And that is really the spirit of all this stuff that you see on the tabletop here. I'm going to give you a few examples of the kinds of dishes that came out of that. This is Ferran Adrià's gargouillou, and he explicitly said that. He said, the gargouillou was amazing. It was, you know, I'd never thought of the possibility of doing something like that, but I couldn't just copy that. I couldn't just go out and pick herbs and spices and put them in a salad, because he's already done that, and I have to not copy. So what he did was take that spirit of finding something new and transformed it in such a way that instead of giving you ingredients as they are pretty much in nature, he's taken ingredients and transformed them so that you actually have no idea what you're about to eat. You know, that plate gets put down in front of you, you don't know what any of it is. You have some guesses, and in some cases he intentionally misleads you so that you're going to guess wrong and be surprised. So he makes it possible for the chef to think, ingredients are wonderful, but we can do things with ingredients that haven't been done before and present states of matter, soft matter, that have not been seen in the kitchen before. And that's kind of what animates this spirit. So that's the Nueva Nouvelle Cuisine, as the New York Times named it. Ferran is especially famous for the foam that he was holding in the previous slide, and also for something called spherification, making caviar-like beads out of anything, pretty much. This is melon caviar. Next week, Joan Roca will be coming here and demonstrating a number of things. One of them, the separation of aromas from the ingredients that you find them in using this machine, rotary evaporator, so that, again, you take a look at these, for example, those white things. It looks like there may be, you know, a champagne or a lemon or, you know, something like that. In fact, they're flavored with chocolate and coffee and passion fruit and tonka bean, all very dark and deep colors, but they've been separated from their colors. So you experience those flavors in a way pure, if that's a reasonable thing to say, you know, without the input of your eyes. So you taste them differently when you taste them without those colors. Jose Andres will be coming, and he made this little bonbon of olive oil that you pop in your mouth. It melts in your mouth. And he made the shell with a material that's used mostly to make cough drops, because it's not sweet the way sugar is, and it doesn't behave in the way sugar does. It doesn't absorb as much moisture from the air. So it's much easier to work with, and you can make things like this and actually serve them. Wiley Dufresne will be coming from New York. Do you want to, are we going to do mokumegane here, or I've forgotten?
It's up to you.
No, we're not. So, but we'll come back to it. Dave is going to demonstrate a dish that he's made using what's called meat glue. And meat glue is what allowed Wiley Dufresne to make these things, noodles that look like noodles, but they're actually pure shrimp, and a chicken McNugget, which is skin surrounded by dark meat surrounding white meat. So you get a bite of the whole chicken all in one bite, a reconstructed chicken. And then Grant Achatz will be coming from Chicago. He works a lot with interesting textures, and this bottom right panel shows you something that I first saw a year or so ago, and I'm still trying to puzzle out, although I understand that someone here at Harvard has nailed it down. How do you pour something onto a flat surface and have one corner make a right angle like that? Soft matter. And then finally, just this year, Nathan Myhrvold, who used to be at Microsoft, has published an amazing compendium of modern techniques, modern understanding, scientific analysis of cooking in a series of books that are just unlike anything else that's been published before. And he is coming later on, I think in November, to give a lecture about heat transfer and about experimenting in the kitchen. And this is just an example of the kind of illustration that you'll find in that book. It's really amazing. 6 volumes of this kind of stuff. So, okay, that's a quick summary of cuisine at the moment, and now I'm going to turn it over to Dave, who's going to show you some examples of these things that I've been just showing you pictures of, although the first one will just be pictures.
Yeah, we're not going to do any plated. We're not doing any plated stuff, so we figured I'd show you something plated that had a lot of different techniques in it that use new techniques. This, anyone familiar with Japanese metalworking? Really? Okay. Well, it turns out that if you take a bunch of metals and you fold them and beat them, fold them and beat them, fold them and beat them, that then when they are sanded off again, you get this wavy wood grain effect, which is pretty awesome, mokumegane. So what happened was a company, Hobart and Star Chefs, another company, came to me and they said, Dave, we will give you a $3,500 slicer if you can come up with a good demo that requires a really good slicer. And so I'm going to show you that demo. All right, so can you fire up the video? Yeah. That's how this world works, baby. Okay, so it's about to go into its thing. Ignore this. We'll talk about that later. That's just onions. Onions, flash-infused onions, yay. Okay. Now, what I'm doing here is, this is going to be a meat glue demo, by the way, in Slicer. I'm making a mold. That's just potatoes and a cutting board. I took, in the school where I work, I took one of the amphitheater's cutting boards without telling them, and I chopped it up into pieces. And I put some of it in the oven because cutting boards become malleable, which I noticed when you put a cutting board too close to the stove, it becomes malleable. So I figured I'd use that on purpose. I'm making a mold here, and I'm going to vacuum it. When it vacuums down, I'll get a mold in the shape of those potatoes, and you'll see why later. The main thing here is a thing called meat glue, which is an enzyme. and it transglutaminases the enzyme, and it has the mystical property that it bonds proteins together. It bonds 2 amino acids together, actually in a covalent bond, and once they're together, they're not going to come apart again. The bond is heat stable. The strength of the bond is similar to the strength of the bond between 2 muscles in a piece of meat, so it's not kind of, it's not horrible, it's not weird. You don't notice that there's a, texturally, you don't notice that there's a glue joint. It's had some controversy recently, but because people think it's some sort of horrible Franken thing, but in fact, it's totally natural. It comes from a soil bacteria that they found, and there's transglutaminase in all of us actually right now. It's part of our blood clotting pathway, although not the actual thing that makes it clot. It's part of your skin formation. It's good stuff, great stuff. So what I'm going to do here to show you how the meat glue works is I've par frozen some salmon and some fluke, and I'm putting it through the amazing Hobart Model 3000 slicer. And when they're all sliced out very thin, I'm just going to sprinkle, and this is the way this stuff works. You just sprinkle the meat glue on like it's a powdered donut or like a beignet. And over the course, it's the enzyme plus some maltodextrin, which is just a sugar, a starch breakdown product that's tasteless and bulks up, and a little bit of casein in this case to help act as a bonder protein. And you put it together like this, and you layer it. What the heck? Can you fast forward to where we were? I did this during the morning, too. I'm horrible with this pointer. I need a separate laser pointer. No, it's like, yeah. No, that's, yeah. Oh, thanks. Oh, this is the blue one? Oh, the green one. Green? Oh, yeah, he needs this anyway. Can you move it forward? That's a fake thing, because I stole it from the Star Chef's website. There you go. Yeah. The little bar. Yeah, take it. Like, no, like, over half. Yeah, more. Yeah, more. Yeah, more. Come on. More. Anyway, while he's getting that, I'll tell you about meat glue. So meat glue, what you do is you put it together, and the reaction takes about 4 hours in the fridge to work. When Wiley's doing it, you saw the shrimp noodles. I'll talk a little bit about those. Since is he going to do that? He's not going to do that actually for the public lecture, right? That one's heat setting. You know, when you heat up an enzyme, until it denatures, it acts faster and faster. So he mixed the enzyme with shrimp and then sprayed it into a water bath where it sets instantly. So meat glue is just fantastic for special effects. Anyway, so here I've layered up the fish, 2 different colors with the meat glue. I put it in a vacuum machine to get the air out, so that even though fish looks like it's together, on a microscopic scale, they're still far apart. So you put it in a vacuum, you suck it down, and now I have a block of fish. I let it sit for 4 hours. I then break it out and let it air out a little bit, par freeze it again, and slice it, and you get this, which is the wood grain fish. And I mean, look, it was worth it. Like, look, I got the slicer. Let me put it that way. So that's that, which is the salmon and the fluke. This is some fennel and apple that I also shaved on the slicer. I did everything on this slicer that I infused with curry oil. These are some onions also on the slicer, infused with vinegar in the vacuum machine, a technique I'll show you later. Creme fraiche with liquid nitrogen pulverized herbs, which I won't demo. Dehydrated, this is like, I think lovage or something. Dehydrated pumpernickel. And these are pressure cooked mustard seeds. So we can go forward to the actual picture so I can see, so it's not so blocky. Next time I'll call Star Chefs and ask for a picture in advance. So here you have it. So you have the base of the fish, which is sliced very thin. You slice it basically like a steak-um. You want the steak-um texture. Steakums, anyone? And then you let it thaw out on the plate, right? You cannot handle it when it can't be handled when it's thawed because it's too thin. And then here you have, this is like tech on a plate here. So this is the 2 different kinds of vacuum infusion, this one with oil, this one with water-based stuff, vinegar, which I'm going to demonstrate later. This is a technique, old technique dehydration, but it's being used by chefs quite a bit nowadays in, not in new ways, I mean, it's dehydration, it's like old school, but it's used a lot on the plate with dehydrated stuff in a way you wouldn't have seen maybe 30 years ago. This is the creme fraiche, but the little dots in it are actually fresh herbs, and this is a relatively new technique that requires liquid nitrogen. You freeze herbs super solid with liquid nitrogen, and then you blend them in a blender, And because they're frozen, they shatter and grind like dry herbs. And then when they thaw out again, they're still green and fresh, assuming you blanch them first. Otherwise, they will turn brown and rotten. This is the pressure-cooked mustard seeds I told you about earlier. They're pressure-cooked in vinegar. Then after they're pressure-cooked, they're drained, and some sugar is folded into it. So they're kind of like a bread and butter pickle, mustard, pop in your mouth caviar thing. So that's that dish. So we're not going to do a plated thing, but I just want to show you kind of like how these techniques can stack together in a dish. Okay? Next, that's the last slide, right?
It is, yes.
All right, so we won't need the pointer anymore. Thanks, Professor. I probably haven't said enough about meat glue, but later when question time comes, you guys can ask me some questions about meat glue. How many of you think it's a horrible abomination, meat glue? Really? I know there's more of you out there. You just don't want to take me on? All right, that's fair. You shouldn't take on someone who spends their days thinking about ways to take you on if you say something to me about it. So one of the things that they're going to deal with a lot in the class is textures and gels and different gels properties. So I took one of my favorite gels, agar, to demonstrate for the class today. And agar is amazing because it's the new class of gels and thickeners that people are using in the kitchen now have the general term hydrocolloid. In general, they get a bad rap because they sound gross, like xanthan and carrageenan, and they've been used for many decades to kind of make food worse, to make it easier to ship, to make it cheaper, to basically either stabilize or reduce quality in a compromised food situation. And what's gone on in the past 10 years is these ingredients are being used not for that reason, but to make things better or more interesting. Agar is a little interesting because although it is used industrially, it's also a traditional ingredient in Asian cooking. It comes from a seaweed. Again, it's 100% natural. Now, because it was school, I figured we'd make a gel from Concord grapes because that's like the school stuff, right? So this is Welch's grape juice is what we made for them. And we're just trying to demo different textures. So this is a set gel. This is 9 grams of agar in 1 kilo of grape juice. So this is basically the texture of an agar gel. Agar gel is very firm. It's elastic in that it doesn't stay deformed. It bounces back. But it's also extremely brittle. When you cut it, you see it cuts very well and it shears very well because it's very brittle, right? So this is an agar gel. Now, another interesting property about agar, you notice when I cut it, it doesn't go back together, and it never will. Once I break the gel, it's broken. But if you break the gel extremely violently by putting it in a blender, we make an entire new category of material. And this is one that chefs use now all the time. This is an extremely popular thing that we call a fluid gel. What do you call it in the science biz, Professor, the fluid gel? Microgel? Microgel. All right. In the kitchen, fluid gel. In the class, microgel. This blender may or may not break. One second. Do. This morning I made a horrible mess. The blender leaked everywhere. It was awesome. Okay, so you have a solid gel here, and then once you blend it, what you have is a bunch of particles, right, of gel that we've broken up, basically in a fluid, and it is a fluid gel. So you can plate this thing like a puree, even though once you put it in your mouth, it goes back to basically being the viscosity of a juice. So a fluid gel is something that has, when it has no force being put on it, has the properties of a gel. But once you apply shear, once you move it, stir it, put it in your mouth, it then takes on the properties of a fluid. This is a thick fluid gel that's used as a puree, and this is one of the main ways we use fluid gels. The other way that we use fluid gels is making them very thin, and that's used for suspension. Anyone remember Orbits, the drink Orbits? That's a fluid gel. Other famous fluid gels, Wiley's fried mayonnaise, which I'm sure he might talk about when he comes. But there's lots of applications for fluid gels in the kitchen. I'm going to show you one more because we were supposed to be talking about foams a little bit. This fluid gel can now be foamed in an ISI thing. ISI, these things, whipped cream makers. How many of you have one of these whipped cream makers? That's it? You should go buy one for a couple of reasons. One, you can make whipped cream, which is incredibly delicious. It is still the best, I think the oldest and best of those kind of foams, right? I mean, whipped cream's pretty, it's good. All right. This is just a foamed fluid gel. When you foam a fluid gel, remember, it's a fluid gel. It doesn't flow to the top of the thing, so before you hit it, you have to go like this. Do not make the mistake of doing that if you've already sprayed it once, and don't hold your hand over it because you're going to spray grape jelly all over the camera. Oops, I didn't screw this on enough. But anyway, so if you, I might not have put enough in. Now I'm going to actually spray the camera, just like I was joking about. Awesome. I didn't put enough in. But you can see, basically, you foam it, and what happens when you foam it is the fluid gel is thin enough to come out of the nozzle, but once it comes out and there's no more shear being applied, it holds itself as a foam. This can also be used to stabilize whipped creams, which is typically how I would use it in the kitchen. So this is 3 ways to use a very simple hydrocolloid. This hydrocolloid can also be used to do spherification. I don't do that, but you can do that. But here's my favorite thing to do with agar. Agar can also be used to clarify. And this is 9 grams in a liter. This is 2 grams in a liter. This is lime juice set with 2 grams in a liter. And this is very loose gel. Can you see that? No. Okay. No. Let me see. All right. So this is a very, very weak gel. So what we're going to do, instead of violently breaking it up like we did in the blender, I'm just going to take a whisk. One of the interesting properties of agar is that it is extremely, extremely porous. It bleeds liquids out. And in fact, one of the old ways of purifying agar was to set gels with agar and then let it freeze and thaw and let the water drip out of it. Okay? So you see we've broken it into kind of curds and whey, and the liquid that's being held loosely by the agar gel now is weeping out of all the places where we've broken it. Which means we can use it to clarify. Let's see. We put cheesecloth around it so it wouldn't look like we were putting it directly through a towel. Did it work? All right. Let me see. Can you see that it's water clear? Now, oh, you can't? I can't see either. Damn. All right. I'll put it into a glass. How about that? When you champagne glass, there's a champagne glass. There. Dead clear lime juice. And still with the flavor of fresh lime juice. If you were going to clarify something that could last, you could use freeze-thaw clarification, which has been around for several years. But if you need to clarify right now, because lime juice that's 2 days old is what? Crap. All right. So, all right. I actually have a better technique than this, but you need a centrifuge. So until you buy your centrifuge, this is the way to do it. You can do this one at a campsite if you really wanted to. The trick to get the yield out of it is not squeezing too hard. That'll eject the agar through it, but gently massaging the sac to obtain the highest yield. This is enough. This is enough of that. Okay. So this is 4 ways of using agar with some kind of, old ways of gel. Fluid gel is a newer way. Clarification, even newer way. So this is, again, the ability to use things that have been around a long time in a new way. So real quickly now, I'm going to bust through 2 kinds of infusion. Any questions on this? We good on this? Look, I know that what I'm saying probably, when you get home, you're going to be like, what the heck was he talking about? You can go on the blog that I write is theoretically more clear because my wife reads it and makes sure it's clear. And it's cookingissues.com. And most of this stuff is on there in some form or another. So we're going to do vacuum infusion right now, which is the same thing you saw in the fish, in the wood grain fish. This is just regular, like, regular puny unclarified lime juice and sugar and a little bit of water. And these are cucumbers. I'll save one that's undone. So the cucumber, the issue with a cucumber, the way you can make a cucumber better is, first of all, to add liquor to it. We're not going to do that here, but I've been known to do it, but is to remove the air and inject a liquid into it. And to do that, we use a vacuum machine. So this is actually a really kind of nice vacuum machine here. Let me see. Ugh. So when I turn the vacuum on, can you see it? Let me move this. Okay, you see how it's starting to bubble a little bit? It's not boiling yet. What's actually happening is the air is being pulled out of the cucumbers. All right? In a minute, it's actually going to start boiling the liquid, even though it's iced down. And the reason is as you apply a vacuum, you lower the temperature at which the liquids boil, right? Which is the reason why when we do vacuum work, we try to keep our food as cold as possible. So I'm just going to sit here for a minute, and only the ones underneath are going to really infuse properly. But I'm just going to let it run for another 35, 40 seconds, and we're going to suck all the air out of the cucumbers. Now, once we suck the air out of the cucumbers, it's covered in a liquid. Liquid is not compressible, right? It's incompressible. So when I let the air back into this vessel, the air is going to come back in, but instead of going back into the cucumber, it's just going to push the liquid straight into the cucumber, and we're going to have a flash infusion. And so this is one of the techniques that chefs use time and time and time again. Hold on, that's probably enough to get the picture. Ready? And you see how you can't see them anymore? The reason is they're camoed. They've been totally infused with the flavorful liquid. Oh, I'm very happy. Look, they look like stained glass or like pieces of jewelry. And this works with basically any. Oh, here's one of the bigger ones so you can see maybe better. Can you see with the light through it? I don't know. They're like pieces of stained glass. And so this technique is a technique that chefs use to get the look of things that are cooked, but with hyper crisp lines and very fresh flavors because they haven't been cooked. They just look like they've been cooked. When you cook something, you also break down the air cells and cause it to look transparent like this, but they're not raw. What do you think? Doing all right? So I'll show you one more infusion technique, and this is something that I've worked on. Unfortunately, we don't have enough to make liquor for everyone, but this is a rapid infusion technique using pressure. So it's the opposite kind of, or an analog to what goes on in a vacuum. In a vacuum, we remove pressure, suck the air out, and then use a little bit of pressure to push it back in. Here, I'm going to use a higher pressure to force a liquid in under force, and then suck it back out again by removing that pressure. So it's the exact opposite of what's going on in a vacuum. So this is coffee, 35 grams of it or so. Then this technique is covered in excruciating detail on the blog. Just look up, I don't know, I think the post title is Infusion Profusion or something like that. I always come up with dumb titles. Okay, so that's 35 grams of coffee, 500 grams of only the best Smirnoff's vodka, the best $12 you can spend. And we're going to use nitrous oxide chargers in the whipped cream. Here's one of the real reasons to buy one of these things, is to do some infusion. Seriously. I mean, that's all mine does at home. Okay. Now, I'm going to put a charger in, and as I put the charger in, we're going to put the coffee and if I can do it, we're going to put the coffee and the liquid under pressure. Is this cross-threaded? Is this going to cause me problems? Oh, there we go. Oh my gracious. Maybe I'll use the white one. Crap on you, you bastard. Shake it. That's a first. I've never had to do that in a demo before. I'm going to put the second one in. All right. Now I'm going to agitate it. And what's happening under the pressure, and I don't think I'm getting the full thing in. Did it feel like I got the full thing in?
It sounds like it stopped.
Okay, okay. So what's happening now under pressure is the liquor is being forced into the coffee because the coffee is porous. Hint, this works only on porous things, right? And I'm going to shake it, and it's going to be forced into the coffee, and I'm going to let it sit for about 2 minutes. And then after it sits, I'm going to violently vent it out. And that's why I don't want to chill this, right? The more it's chilled, the more soluble the nitrous is going to be in the liquid. And so the less violent bubbling I'll get. And my theory, unproven, is that the actual more violent it gets, the more flavor you're boiling back out of the stuff. Right? Make sense? No one's ever come up and said I'm wrong in any sort of way that makes sense to me, although I'm willing to be proven wrong. Has it been 2 minutes yet? Okay. What?
Have something to drink.
Right. I'm terrible at calming down. Okay, so while we're doing that, maybe I'll start on the other drink. Do we have time to do the second one real quick?
Yes.
Okay, so I'm going to talk a little bit about carbonation. Now, how many of you out there own some form of carbonation rig, SodaStream, blah, blah, blah? Good. Good. How many of you own a 20 or 5 pound CO2 tank? All right, that's the way to go. That's the cheap way to go. No offense to the SodaStream. A 20-pound CO2 tank will carbonate 200 to 400 gallons of product. Okay? So it really is economical in the long run and fits underneath a standard counter. So you know. But you can carbonate in one of these. It's just the problem is it's very, very wasteful. Now, when I did nitrous, I used nitrous oxide here. And the reason it's used in whipped cream is that nitrous doesn't have the prickly sensation in your mouth that CO2 does. So when we don't want to have a prickly sensation, we use nitrous. And that's why I use it here. I don't want any residual carbonation taste in my liquor, right? If you want carbonation, obviously, you're going to use CO2. Now, the reason I clarified the lime juice, right, is so that I could do a good job of carbonating. If you were to take regular lime juice like this and carbonate with it, it would spray everywhere when you're trying to carbonate, especially if you were trying to get something really bubbly, like a gin and tonic, for instance. So in order to get really high carbonation, you need to do clarification. That's why I spent many years and many thousands of dollars trying to work on clarifying things. So anyway, so let's carbonate something. Is this lime juice? Yeah? Let's see how she tastes. Yeah. Another good thing to remember about carbonation is if you're going to carbonate liquor, which I highly recommend, you need to add more bubbles, more pressure, more CO2 than you would if you were carbonating a regular liquid. And the reason, water I mean, and the reason for this is that CO2 is more soluble in alcohol than it is in water. And so to have the sensation isn't because the stuff is soluble. The sensation is because the CO2 is coming out of solution onto your tongue. So you need to put more CO2 into alcohol to have the same level of bubbliness than you would in water. So so for instance, if you're going to force carbonate wines, you're going to carbonate at one pressure, roughly 30 to 35 psi. If you're going to do sake, you're going to go about 5 psi higher. Mixed drinks, we tend to rock around 40 psi at 0. It's also temperature dependent. Everything's everything dependent. Temperature dependent, pressure dependent. Okay. I'm going to do gin and lime juice. I didn't bring my quinine with me. I didn't feel like bringing a bitter powdered substance back from Colombia, where I just did my last demo. It just seemed like a really, really bad idea. Has that been 2 minutes yet? Yeah. All right, hold on a sec. I'll make this, and then I'll ice it down and carbonate it after I show you this thing. See how this tastes. I'm only making one. The other thing about carbonation is that people are used to drinking carbonated beverages that are fairly low in alcohol, and carbonation increases the rate of alcohol delivery to your body. So you're going to want to go ahead and water them down a little bit, or people will be on the floor. which I've done. Have you ever had? I've once carbonated bottle strength gin and tonics, and it was absurd. I actually redistilled the gin to get it above bottle strength, so that when I added the lime and the tonic and all that, and the sugar, it would come back to bottle strength. And it was only tasted good at exactly minus 18 C. Anything else, no good. And it was just a horrible, drunken thing. Okay, ready to vent. Always put something over the thing because it's going to make a mess. Vent violently. Nice. Oh, by the way, when one of these things suddenly stops like that, it means that you've blocked it. Don't trust it. It's going to spray all over your jacket. There we go. Good. Okay. And coffee. So this is cold coffee done extremely quickly. Look, learning about how to infuse things rapidly is so interesting to me, because what flavors you pull out of a product are dependent on time and temperature and pressure. So you can extract different products from something depending on how they're extracted. So very short extractions on things like cocoa nibs tend to not favor the bitterness in them. And so you tend to get more of the chocolate notes and less of the bitterness. So you can do low sugar things. So I don't think that these kind of infusion techniques are better, or like old style long infusions or this. It's not a better or worse, they're just different. You know what I mean? It's a matter of choosing whatever works best for the application. Where am I going to put this? We don't need this anymore, right? All right. That's a horrible waste. Okay, so I'm going to make a quick drink with this, and then we're going to carbonate, make a quick drink, and then questions and out. Yes? Yes? I normally hate creamy drinks, but this one's okay. It's one of milk, one of cream, 2 of booze. I did this one for the Colombians, and they dug it because, you know, coffee. Come on, really? It's almost there, guys. I know you can't. I don't want to stint on the coffee, though. The coffee's the money. All right, there we go. And I'm using a rich, simple syrup in this because I don't want to add any more water than is necessary, because I've already diluted it with milk and cream. Also, you're going to want to use cold milk and cream because, duh, it's milk and cream, but also because it's going to dilute less when you ice it down. I add some sugar. I'm going to go a little light on the sugar. And I'm not serving you, so I'm not using gloves because I can't find them. I could sit here and talk for like a couple of hours just on the ice and the shaking and whether or not it makes a difference. So if any of you guys are bartenders, we can come up and argue about it later, all right? Oh, coffee and milk are great like this to shake, even if you don't have alcohol, because it rebodies it. I drink only espresso, and I like the body of espresso. And so shaking drink brings back some of the body of an espresso-based drink. You like my fancy serving cup here? Only the best. Anyway. It's good, right? It's good, right? Can you just have a quick? Give this sucker a quick rinse for me. I only brought one set of cans. Okay, last up. We're gonna. I'll just carbonate in the thing. I'm gonna carbonate in the thing. Okay. I'm gonna shake it actually in the container. That's what I've decided to do. So I just made her wash my cans for nothing. Don't tell her when she gets back. So one of the interesting things about shaking a cocktail is I'm sure all of you who bartend will think that the longer I let it sit on the ice, the crappier it's going to get. And this is true over long periods of time. By crappy, I mean diluted. And but the truth of the matter is that over short periods of time, you get very little additional dilution based on the ice staying there, because it's only dependent upon how fast the heat is leaking out of your system. Right? Also, the size of the ice doesn't really matter in terms of its chilling capacity. It only matters in terms of the surface area of the ice. But again, this is an argument I'm willing to have for the next 3 hours with anyone who comes down afterwards. Wrong container. Oh, man. I have no idea what this is going to taste like. Also, we were supposed, in the morning we did liquid nitrogen as one of our things, but we're not doing the liquid nitrogen ice cream, but we're still going to serve you the liquid nitrogen marshmallows, yeah? So, while I shake this, do you want to describe what's going on with the liquid nitrogen while I shake this guy? Like the water and the blah, 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 blah. And then you guys can start ramping up the liquid nitrogen, the crew.
Well, I'll try to do what Dave does much better, description of what's happening with liquid nitrogen. But so liquid nitrogen is what, close to minus 200 Celsius, very, very cold. But its chilling power is really not that much more than ice, because it's not as dense. Doesn't have the same heat capacity. So you can put something in it that doesn't have a lot of water, which has a very high heat capacity and therefore will get very cold, and freeze it in liquid nitrogen. It's very, very cold, but if you pop it in your mouth, because it's essentially air and a little bit of gelatin, it just goes away. And so you can put marshmallows in liquid nitrogen, get them very cold, put them in your mouth. Your mouth gets cold enough that you essentially breathe vapors out of every part of your mouth and nose that happens to be open at the time. It's a lot of fun. In fact, the first guy who did this in a restaurant designed it as a palate cleanser that was also kind of a mind cleanser. This is Heston Blumenthal is his name. He has a restaurant called The Fat Duck, and I happened to be around when he was developing this. And the idea was, you come into the restaurant, he's out in the countryside, so it's been a long drive from London, you're probably late, you may have had an argument in the car while you were getting there. He just doesn't know what kind of state of mind you're arriving with, and he wants to kind of reset everything in you. So he developed this palate cleanser, which is essentially a meringue, like a marshmallow, but flavored with lime and tea and vodka. And he freezes these little meringues table side right in front of you, pulls them out, drains them, gives them to you, and everyone at the table gets one. You pop them in your mouth, and you're all snorting vapors all over the place. So the shock of the cold, the acidity, the astringency, the alcohol, the whole thing, and you just all break out laughing because it looks so silly. Now you're ready to sit down and have his meal. So it's a brilliant use of what liquid nitrogen does very well.
Back on the carbonation for a minute. Did you guys notice that I threw one charger into it and then vented it out pretty quickly afterwards? Those of you who noticed, I did that. This is an extremely expensive way to carbonate. It's okay for home if you just want to be fancy for a night and you do a little bit larger quantity than I did. One of the main problems with carbonation is you need to get rid of the head space when you carbonate. You need to get rid of the air in there. The air that's in the head space is kind of doubly bad. One, it's taking up space that could be taken up by carbon dioxide, which is greatly soluble in the liquid, whereas the air is not, by and large, being mainly nitrogen. The other thing is that shaking the air into it generates lots of little nucleation sites that cause more foaming. So you get doubly shafted, 2 times shaft. So what I do is I put one charger in, lightly whiz it around, vent it. That gets rid of a lot of the nucleation sites and air that are present in it, and then I throw my carbonation charge on it. I'm going to lightly vent this. Harvard requests that I wear safety goggles, and rightly so, when I'm using liquid nitrogen. I'm just going to chill this glass. Are we ready to do the marshmallows? Let's just start dumping liquid nitrogen into them. Okay. I just noticed, by the way, I didn't plan this. I just happened to notice as I was walking, doing the demo. Where the? Oh yeah, look at this. I had no idea. How ballsy is that? Look at that. The strainer fits right over the edge of the ISI. I'm also going to chill champagne flute with liquid nitrogen before I hand out the liquid nitrogen, because this is the way you should chill champagne flute. Here's your, right? Just, a little bit of a swirl. You can do 2 at a time, and then get a rack of champagne glasses, and then just dump from one glass to the next down the line. And if you do that, it's pretty quick, and it's about 10 cents a glass, I think we last calculated is what it is. Now I have a nicely chilled glass that won't leave a ring on the table, and that won't make my hand cold, and only the inside's chilled, not the outside, so it's not going to stick to my lips. And see whether this thing actually works here, huh? Oh, yeah. Gin. It's actually not really a tonic because there's no quinine, but it's gin and tonic similar. And you wish you were me. All right. So I think we're going to serve marshmallows and questions, right?
Here's to that.
Yeah.
This is really good.
Great stuff.
Which one do you want? Coffee or gin?
I want that one.
All right, I'll pour you some more.
So while we are preparing the marshmallows, we have a little time for questions. Also, I should say, outside, these are the aprons that we made up with all the equations from last year. You can get them outside. You can buy some, and also there'll be a book signing by Hal and his book outside if you're interested after the talk. So we have time for a few questions.
Delicious.
Can you repeat the question?
The question was, how does a wood grain fish taste? And I gave the pat answer, which is delicious. It's true. But the fact of the matter is that we had to run through a bunch of cycles of it before I got it delicious. Meat glue, transglutaminase, has as a byproduct that it produces a slight amount of ammonia in the reaction that flashes off during normal like airing. And the first time that I made it, I was so nervous about it sticking together that I over meat glued it and then didn't allow the fish to air off, right? Now when I do it, I use a very small amount of meat glue, and I cut the bag off right after it's been suctioned down so that it can air out while it's doing it, and there's no trace of ammonia. The fish itself it's fish. It's delicious. I didn't tell you this. I sprinkled salt and a little bit of sugar, almost like a Gravlax cure, on the salmon, so it's not a totally uncured salmon. I forgot to mention that. So it has a little bit of a cured taste to it, and it's great. I mean, it's like you would normally eat those 2 pieces of fish, just in a new form.
Okay.
Oh, by the way, I'm being told to tell you that I'm going to be back for a drinks public lecture that's drinks only sometime in November. November what? 10th. Okay.
I have a little question and a little comment. The question is that you said you can substitute nitrous oxide for carbon dioxide. Now, nitrous oxide is if I remember, is a laughing gas.
Yep.
And also it can be converted into nitrogen dioxide, which is a base of nitric acid, which is extremely poisonous. If those effects come into, in your practical observation. My comment is this. The gentleman early on mentioned that Thomas Jefferson put a spoon of oil in 1 acre of lake, and basically 1 nanometer of thickness can be detected. I recently invented a new technique where you can detect 1 molecule of sugar in a lake of Lake Michigan. It's called chemiluminescence technique. All right.
Oh, regarding the nitrous, just to answer the comment on the nitrous, N2O is commonly used in the food industry and has been for years for whipped cream. It is, in fact, laughing gas, which is why most college students who buy whipped cream aren't using the cream. you'll see that when I use whipped cream, I follow the instructions to turn the unit entirely upside down. Whereas if you go like this, you get the other effects. I happen not to like it as a drug, but there you have it.
So you were talking about cooking with pressure cookers. I'm over here. You were talking about cooking with pressure cookers, and then you were demonstrating techniques with vacuums. Has anyone worked on cooking in vacuums, and would that even make any sense to do that, to try to do that?
Many people have. There's people who, like the one you can go buy commercially today if you have a lot of money is called an AccuSteam steamer, and it steams at a reduced temperature by putting a vacuum pump. I don't understand quite the advantage of that as opposed to just controlling the temperature accurately. Vacuum frying is a technique that's used industrially so that you can get the crispiness by getting rid of the water at lower temperatures. So that if you want to make an apple chip, let's say, which has a high sugar content, if you fried it traditionally, it would brown too much. If you fry it under a vacuum, you can get the similar crunchiness, but without too much browning. So vacuum is used for that, and vacuum ovens are used to set things. Yes, so there's many things. It tends to be more difficult, especially because once you suck a vacuum, you need to then, if you really want to do a good job, put a cold trap on it to recondense the moisture, so it tends to be more technically difficult. There's a famous piece of equipment called a gastrovac that I happen to think, I'm not going to say anything about it.
No, go ahead.
Browning distilled the juices, which I actually saw quoted credulously in the New York Times in the last week. Are the techniques pernicious, or just the theory about what happens?
No, it's the theory. I mean, browning is great because it generates flavor. But it's a mistake to think that browning is going to do anything for juiciness. Juiciness, the texture of the meat, is essentially a function of temperature. And so you don't have to even worry about what happens to the surface. If the inside is at 140, it'll still be kind of juicy. The moment it gets much above that, it's dry. And it doesn't matter what searing is done or not done. Yeah.
Any other questions? Yes, Mike.
I was just curious, as you experiment with different things, how often do you make something that tastes good versus how often do you end up with something that's not?
Okay, that's an excellent question. Very often things taste very bad, but I think this is the case with all food. The question is, can you learn from what you do, and can you find the nugget of what might be delicious in it and then adapt it for later? It's very, I mean, look, often there's times we're just throwing stuff up against a wall and we're like, but you know, there's usually something you can learn. For anyone that's really interested in seeing how someone at the top of their game works, and I know he's coming here, there's a new movie that trails Ferran Adria and El Bulli, and if you're not a cook, I can see how it would become boring to see someone eating food for 2 hours. But as a cook, I felt I learned a lot about even his process, because he's so hardcore. You know what I mean? So if you want to see kind of the yes, no, what's going on, and then working, that movie is a good place to see someone doing it in the real life who's, you know, at the top of the game in the whole world. So, I mean, again, if you're not a food person, might be bored, but interesting for that.
One last question. Can you use the microphone?
As I understand it, if you cook dried beans at too low a temperature, you end up with something that's poisonous. Are there cases like this where experimenting runs into problems where you end up with poison chemicals because of some reaction that you've created?
Well, I mean, low temperature cooking does, if it's low temperature enough, does raise the possibility that while you're cooking whatever it is you're cooking, you're also culturing microbes. And you do have to, if you want to experiment with that kind of thing, then it behooves you to find out, you know, what those limits are. They're fairly well known, and so if you cook at low temperatures, you just cook longer to make sure that you're taking care of that problem. As far as beans or a particular food generating toxic compounds during cooking, I'm not aware of anything like that.
Chefs use ingredients that are straight up toxic that are traditional. And one of the problems is when a traditionally toxic ingredient is taken out of its context and then used in a new way, if you don't pay attention to what's going on. Tonka beans are an example that are toxic and are being used by chefs, but as, or like apricot kernels, which can have a good amount of cyanide in them. So these are all traditional and are used traditionally. The question is when you adapt them to new techniques, are you paying attention to the traditional things that hold you back from hurting people or not? And it's an interesting question.
Okay, so at the back, they're still making some liquid nitrogen marshmallows, so if you want to blow some smoke, you should do that. This is just nitrogen smoke. You can do that legally here. In the meantime, please give both Harold and Dave a big hand. Thank you.
Thank you. Thank you. Thank you. Thanks a lot.